A very good morning to all of you. Myself, Anil Kumar, here present with you in front of you to cover one topic under AMRUT program. The topic which I'm going to cover is already displayed. It is survey techniques and navigation systems based data collection for AMRUT program. I hope my video and sound is okay. Please confirm. So under this program, as I mentioned, the survey techniques and navigation systems based data collection. So basically, when we talk about the data collection, I'm talking about the spatial data. That means X, Y, Z coordinates about an object on the ground. So we can collect these coordinates either through conventional survey techniques, or nowadays presently we can collect through navigation system based approaches to prepare map or any other information. So what is required to prepare a map? When we are preparing a map for AMRUT program or for any application of urban, basically to prepare a map, there are two components. One is measurement, where what is where. That means which building, which road, where it is located. So location has to be defined in the form of X, Y. That is planimetry information, or called latitude and longitude. And second parameter is height. So these X, Y, Z parameters helps where is that object. Identify what is what. This road is this straight line is a canal or road or railway track, that has to be identified. This rectangular building is a ground or it's a building or something else, so that has to be identified. So that is what is what. So two things we have to do. One is to locate any object with the help of coordinates, and second is to identify what is that object. So if you talk about the conventional survey methods, there are basically different techniques developed under surveying where we can get the coordinates. There are different types. One is survey, that is traverse survey, and second is triangulation, and third main dedicated one is plane table survey. Traverse survey means there is some ground. Along the boundary of the ground we do traverse as a open or closed traverse, and using this measured boundary along the area, we try to map the area. Second is triangulation. So triangulation means we want basically height of an object, or we want the coordinates of different ground receiving stations developed or established in the ground. So for that we can use the triangulation approach. Suppose this can be area, and here before we start the actual survey with the help of plane table, we have to establish the ground control points. So these are the ground control points, and there we can mount some small towers. So from this point we can measure this point and this point and maybe this point, and we can make triangle like that. So we can fulfill the condition of the triangle, so that finally we, using the horizontal and vertical angles, we can get the coordinates of this point with respect to this. We can assume this coordinates to be 0, 0, 0, and then we can get the coordinates of this point. That is only possible if we have the horizontal and vertical angles of this point or this tower from this point, and same way for this, the horizontal and vertical angles of this point can be calculated with respect to this. So once we know the angles, we can know the base length of one triangle, with the help of that base length and the other angles, we can go on finding out the coordinates of other ground control points. So once these ground control points are established, we can use plane table survey in this area, and we can take this point as a station. We can mount the plane table in this area, and we can start plotting the objects, whatever objects are visible in this area. Now, before plotting, we have to orient this table. This table we can orient using these points which are visible in this area. So the purpose of establishing this ground control point was that we can plot these points on the table first, and we can orient the plane table wherever we mount the plane table at a given station. We can orient first, and then we can start plotting the features on the plane table. So that is the basic conventional survey technique or methods to plot the objects on a paper. And here, when we are plotting, we are basically doing linear measurements. We have done angular measurements and height measurement to plot or to calculate the coordinates of these ground control points. So here, if you talk about the linear measurements, there are different instruments developed in surveying. One is chain survey we can do. More comfortable is tape survey. Nowadays, there was era to use EDM, electronic distance measurement instrument. So what it does, it gives you the distance from a given point to other points. We can directly fire the radio waves and we can get the direct distance. Nowadays, there is an era of GPS, and now this is called with a new term called GNSS, Global Navigation Satellite System. We will talk about all this. Here you can just see how with time the different instruments has changed for linear measurement. Then there are instruments which is required for angular measurement. The very basic one is compass, but compass is not used. Compass is used for get the magnetic direction from the magnetic north, but it is not useful for preparing the map. So basically, to get the direction, we have to use theodolite to get the angles and establish the ground control points. With the help of ground control points, we want the direction from the true north. So that is feasible or possible using theodolite concept. Third level of measurements is height measurement. So for that, we can use dumpy level or auto level. They are the main conventional instruments under level category, and they give the height of different points from the reference point in the given area. Second, if we don't have the dumpy level or auto level, we can work with the theodolite as well as digital leveler. So it is a modified form of dumpy level or other auto levels. So this is a digital form. It is easy to work. We can store the data in the memory, and later on we can download the data in the computer or laptop. Nowadays, you have a universal machine which can do all the tasks of surveying, and this instrument is called total station. It is coming in two categories, as a mechanical total station as well as robotic total station. Both these instruments we have in our campus, and sometimes if you visit, we can show these instruments, mechanical and robotic. In the mechanical, minimum 2 people are required at a time. In the robotic, single person can operate because our machine is kept in the auto mode, and we can go to the reflector to start doing measurements. But in the mechanical, there should be 1 person at the machine and 1 person at the reflector. So minimum 2 persons are required. This takes little more time in the ground for observations, and this take less time. But of course, this is more costly. Anyway, if you talk about both these machines, they have very basic common components. One is electronic distance measurement device, which gives you the direct distance. Second, it has theodolite, which can measure the horizontal and vertical angle. It has an auto leveler, then microprocessor to process the data coming from EDM and theodolite, and to give you the coordinates of the remote area as well as the length and area of in the study area. Then it has a battery and spare parts to provide the power and run the machine. So here you can see already listed, mentioned. There is manual robotic total station, and we can take robotic total station. So we can have manual category, or we can have robotic total station. Of course, the cost wise, if you see, this may come 4 to 6 lakhs. Within this range, you can easily get the manual total station. The robotic may cost you say 12 to 15 or more lakhs, depending upon configurations we are asking. Basic components of a total station, it can be manual or robotic. There is a prism reflector. It is a combination of ranging rod, staff, optical, cuboidal, mirror, having 2 to 3 lifts with 5 centimeter interval graduations, adjustable height from 1.5 meter to 3.75. So you can adjust its rod where the mirror is kept, and the rod height you can change from 1.5 meter to 3.75 meters. More number of prism we can use, so that when you are covering very large area, you can maintain the accuracy. So you can use minimum 1 prism, or you can use minimum or more than 1 as a 3 prism. These total station can work without prism also, up to distance of say 1000 meters or 1.5 kilometers and so forth, depending upon the surface, how much it is reflective, so that some energy can be recorded by the instrument for measurement. More accuracies can be achieved from these instruments while taking care of some of the things, like careful centering is done. Centering means this is the instrument center here, and this is the ground, and here this is the point we are measuring. So this point of the instrument should lie exactly on the top of this point. That is called centering. Accurate point target. So when we are recording the reading of any point through a prism, so we should exactly target at the center of the prism. It should not be deviating. Average of multiple points. So we can take multiple points at a given point observation, so that the average observation can be calculated. A better optical lens. We should have a strong tripod. On the tripod on this instrument is kept, it should be strong enough so that it is not shaking or no vibrations are coming from the ground. Verticality of the prism pole. So where this prism is kept, that is split bubble. So we should see this pole is always vertical. Angular accuracy from these instruments we can achieve in 2-3 range, say 1 second to 20 seconds. The best nowadays is 1 second, but if our requirement is not 1 second, we can take little lower grade instrument, but best we can achieve 1 second angular accuracy. In the linear accuracy, we can achieve nowadays 2 mm to 10 mm per kilometer. At a per kilometer, the error can be 2 mm to 10 mm depending upon the capability of the instrument. So you can see some of the models like Nikon or Leica, they can give you 1 second angular measurements accuracy. With single prism, you can achieve 2 mm plus minus accuracy in XY and Z. With 3 prism, you can achieve plus minus 1 millimeter level of accuracy. Distance wise, you can go like if you are going up to 2.5 kilometer, you can use single prism. If you are going 2 prism, that means you can cover the distance 5 to 10 kilometers, 5 to 7 kilometers. And with 3 prism, you can go 10 to 12 kilometers. And this large number of distances you cannot measure in the flat area. But when you are at the hilly terrain and you are measuring the distance from hilltop to hilltop, so there you can cover a 10 kilometer or 12 kilometer, not on the plain ground. Please remember the different terrain has application for measuring the points. Function of total station, it can give you the angles as well as distance, and it can record them, correcting the measured distance with prism constant, atmospheric corrections, temperature at the surrounding, earth curvature, refraction corrections due to the atmosphere, since we are covering large area, computing the point elevation, computing the coordinates of every point. It can give you the elevation of any point. You can read on the screen also, you can store it. It can compute the coordinates XYZ of every point which is measured. Remote elevation measurement. Remote means there is a tree in your study area. You want to map the height of a tree, and you can't climb, so you can shoot that height from this instrument, and the instrument will on the spot will display you the height of the tree. So which is a remote access, actually remote area, you can't reach there, still you can do measurements. Area calculation you can do. Any field has been measured, you can find out its area in the ground. Data transferring facility from instrument to software, or to laptop or PC, or from laptop or PC to instrument. You can use just pen drive. You can copy your data in the pen drive, and through pen drive you can upload or download the data in different formats like AutoCAD DWG format, or DXF format, or shape formats. Shape can be 2D or 3D. Format of conversion, so you can convert the data into different formats as well as the units. If you have measurements in feet, you can convert that into meters and so forth. Application of total station, it has very strong application, specifically when you want to do measurements for a small area with very high accuracy. So total station is the actual instrument. You can use it very easily. Like a few applications I've listed here. Updating the map, some previous map is there in the raster, in the vector format. You can upload that map, and then you can update the map. Topographic survey, specifically for small area within city or the complete city, you want to do measurements, you can prepare the topographic survey at the ward level, or the unit level, or at the city level. Of course, little time consuming, because you have to measure each and every point on the ground, and a number of times you see issues that person cannot reach the point, or you require approval from the concerned property owner to climb on that property and take the measurements. Then cadastral survey for urban, rural, or agriculture fields, you can prepare very easily the cadastral survey. Project construction survey, some construction is going on and you want to monitor the construction, you want to prepare the plan of that project, you can do that. Very good application in the road and railway survey, railway tracks, if it is a new one or the existing one. In both the cases, the total station can give you the very good measurements up to millimeter level. Mining survey, daily basis, you want to see how much excavation has been done in the mining area, that can be monitored with the help of total station. So advantage of total station is you can measure say 500 meters or up to 1000 meters without a prism if the surface is reflective. And what you can do, you can make the grids every say 1 meter. It can give you the measurements on the wall or on some hilltop, and you can see how much excavation has been done. So this may take just half an hour, and you can scan the complete that area, and you can see today in the morning if you can scan, and you can prepare its mesh in the evening, and if you take the difference, so you can find out how much volume has been excavated. So these are the advantages you can do also through total station. Operations involved while using total station, there are different steps we have to follow before we should start the observation from total station. One is establishing that site data. So you should know the coordinate system, on which coordinate system you are doing measurements. It can be default 00 local coordinate system, or some GPS coordinate system. If you are taking, then you can see on which datum the coordinates are, and then establishing the north. So with the help of, there are different methods incorporated in the total station. You can have the default north direction, or some single backscatter, backsighting observation you can do, 2-point problem you can do, or some already feature which has been surveyed. So with respect to that, you can orient the total station. So that is meaning of establishing the north. Setting up the total station, you have to place the labeling, the tripod on the datum. So if you have some point as a reference point on this, you have to put the instrument through tripod, placing and labeling the gun on tripod. So you have to put the instrument, and again you have to see the labeling and centering. So it is centered, and here if you see the split bubble, it is perfectly labeled. So two things has to be seen. Linking the data connected to gun. If you want to download the data or upload the data, then data collector, you have to go to the main menu go for the basic settings like your pole height, how much the pole height is, what is the height of the instrument. Then the coordinates you are going for orienting the instrument with respect to back sighting or with respect to 2-point or 3-point problem. So all that settings you can do here. Creating a new job file, you have to create a new job file, or you can use the existing project file if you have. Then shooting the points, identify the important points to shoot. That means you have to identify in advance the points which has to be measured once the instrument is oriented and all the setting has been done. Then you can start doing measurements on different points to get its XYZ coordinates. So identify the important points to shoot, shooting the points, record the points, shooting additional points. You can consider more points as an additional point in the field, noting the special features, name of the features or the objects you can identify, and you can feed them as a field. Post-processing means you can download the data and you can convert to different units if you want. And later on, you can edit the map, edit the data, and you can plot or map generation can be done. So these are the basic broad steps you have to follow while using the total station. So this is all about a total station. Next is I'm coming on GPS. As I told you, from 1995 onwards, there is a common term GPS, Global Positioning System. Nowadays, from last a decade or say 5 years, people are talking about the different terminology for it. They call it GNSS. GNSS. This means Global Navigation Satellite System. Why it is called, we'll see in the coming slide. So let's try to understand about positioning system. With age, if you see, people were meandering from their campsite to some site for hunting, and they may be recording some main features like some boulders or a prominent tree or some hillock or some dry river. And if they follow these attributes in the reverse mode, they can reach the campsite. So this is a positioning system again, which is used in the navigation, and they can reach the campsite. Second is, if they are moving on the water surface, question comes, where is the landmark? So there is no landmark. So people have seen upside and they have noticed the natural planets. And with the help of these planets, if they have done very good, very accurate measurements, they can use these planets to find out their position in the form of latitude, longitude, and height, as well as they can also get the time. The example is sun clock. So that was the star age. But here more very critical expertise is required, and at different areas, different planets are visible. So people should be aware about these planets, and they should be aware how to do measurements. Third is the radio age, when people want to communicate and transfer the data. The positioning system, people use this radio age system to get the coordinates or locate the object. Here you can see one live example also. When the police detect a thief, they basically record the thief is making a call, and call is picked up by this tower. So from this tower location, they can find out what is the distance from the tower to this person. That is called range row. So police can say the person is at a distance of 3 kilometers from this antenna, and this antenna is located in a particular locality. So in that locality, they can say a person is in the range of 3 kilometers. But if we have some device here, that simultaneously we can receive the signals from two different antenna. So then these two rays will intersect at point P or at point Q. So now we can narrow down the person position from millions of points here on the periphery of the circle to just 2 points. But if we have one more tower here, and its signal is also recorded here or here, then we can pinpoint the person is at 1 point only. So if simultaneously we can have the signals from 3 different antennas on the ground in the radio age, so that we can locate the person position. But this system becomes again complicated when it's covering to a very large area. Every 300 kilometers we want one tower. And like in the India terrain, area covered is very large, thousands of kilometers. So these antennas will be required large in number. Second thing, when we are on the water body, so there we have to make the artificial platform where we can mount these antennas. So that is, this again is little typical, a little difficult task when we are covering very large area. But fourth age is the satellite age, where they have used the concept of star age as well as the radio age using the satellite. So here the artificial planet has been replaced with artificial natural planets has been replaced with artificial planet. One. Second thing, these antennas are not mounted on the ground, they are mounted on these platforms. So if we have 3 satellites in my area, so I can get the signal simultaneously from these antenna, from these 3 satellites, and they will intersect at one point. The moment they intersect at one point on the ground, I can get the coordinates of this point. So the concept is same, only thing, these towers are not on the ground, they have been taken in the space. The very beginning of GPS was to detect the defense vehicles in the air, on the ground or on the water surface, and the initiative was taken by USSR. Their system was called GLONASS, which was not initially fully operational, but now they are trying to make it fully operational. But the first application you can see for GPS was navigation purpose. You take any GPS constellation or navigation satellite constellation, they have 3 segments. In the satellite constellation, large number of satellites are required, not one satellite system, because at any given point we require minimum 4 satellites for 3D and minimum 3 satellites for 2D. Why? Because we have total 4 parameters which are unknown. One is 3 is XYZ, and 4th one is time error between the satellite and the ground receiving station or ground receiving GPS receiver clock. They have a time offset, so that has to be adjusted, and so we have total 4 unknown. So for 3D, this is 3D observation. So for 3D observation, we require minimum 4 satellites. This is the 4th unknown. And for 2D observation, that's we want to XY. We want, in that case, we require 3 satellites. So it is not a single satellite game. This requires large number of satellites. Anytime, anywhere, if anybody wants to do observation, the GPS signal should be available. Between GPS and user, this is one. The user can be on the air, on the ground, or on the water surface. We can get the coordinates, and there is one-way communication here, not two-way. Here you have two-way communication. They goes on downloading the data from satellite, and if some corrections are required, they can upload the data from ground to the satellite. Here there is no communication required between user and the ground control segment. You can see the ground control segment distribution for USA based system, that is Navista satellite, and from there we got the very common term GPS. So these are the 4 islands under US defense, and they are used also as a monitoring station. So that means same satellite is monitored in the same day from different areas, and this Colorado Spring work as a monitoring station as well as the master control. So if some corrections are required, the master control takes care to apply the corrections. For IRNSS, Indian Regional Navigation Satellite, you can see this also has different referencing stations on the Indian region, and they are basically again monitoring the satellites, and they transmit the corrections to the master control, and they can apply the corrections if required. User segment, if you see in the case of GNSS, it can be any user on the pole in the night time, or on the water surface, in the air, or on the ground during rainy time or during cloud. They can do measurements. So it is 24/7 facility available for getting the coordinates and time. Basically, how to get the coordinates? When we receive the signal, the signal has 2 main informations. One is like here carrier frequency, which talks about phase of the signal. Coarse acquisition, which talks about the time of the signal. Precise, again, this is not accessible by the civilian users, and the satellite message. So this is called ephemeris or almanac. So this talks about the satellite coordinates, at what time which satellite is available where, and the health of the satellite, and so forth. So using this information, which is modulated on the two signals L1 and L2 in the case of GPS satellites, we can do two type of measurements. It can be code measurement or carrier measurement. In the code measurement, we record the time, and with respect to time, we can do the measurements. In the carrier measurement, we record the phase of the signal. So using phase information, we get the coordinates, first range, and then with the help of range from each satellite, we can get the coordinates. The satellite message, basically from here, this is also called technical term as almanac or ephemeris. So this talks about what are the different satellites available in my area at a particular time, their coordinates, and how they are distributed. GPS equipments now, if we come to the first category, we can have the handheld GPS receiver. This is like a mobile phone nowadays. The cost may go here 5,000 to 40,000 depending upon configurations. You can see small antenna sometimes outside, sometimes totally inbuilt in the machine. There is a display screen, alphanumeric keys, and function keys. So function keys and alphanumeric keys are required to set up the machine with respect to different coordinate system, date, time, station name, and so forth. We can enter through keyboard, and they work with a single pencil cell to 6 pencil cells. Sometimes they may have facility to connect the external dry nickel cadmium battery to work for continuous for different hours. So that is possible, but not all the models. We have to see which model is having that facility. So accordingly, the cost increases as we talk more features in the GPS handheld GPS receiver. Second is multi-component. Very common term is called geodetic GPS receiver. And here you can see all the components are different. The dry nickel cadmium battery is around half kg, which is physically separate identity. Processor is there. Control unit and antenna is again separate, which is here mounted on a tripod. We can mount on a telescopic rod of 1 meter, or we can mount on a 2-meter pole and so forth. Or we can make it permanent location of the GPS antenna. So as per the application, we can use it. But here you can see all the components are different, and they are called geodetic GPS receivers. They have two subcategories, either single frequency or dual frequency. So some of the makes of these instruments we can see here, like handheld one, Michelin company, Michelin Sports Track, Garmin E-Tracks, and Garmin GPS Map 76. They are very old GPS models. As per my knowledge, people are not using much. Anyway, I'm just showing you a few of the models. So these are again for the few models of handheld GPS receivers. Then geodetic one, you can see here antenna on a 2-meter pole. This is a control unit. This is a terminal unit, and or the processor, and this is your basically radio beacon to apply the corrections. You can mount the same antenna on a tripod. You can have the GPS from Trimble, also again a 2-meter pole. This is an old one, old GPS 500 series from Leica. This is a control unit. This is your receiver. This is a beacon. Again from Leica, geodetic GPS receiver. Outside they look same. It is single frequency or dual frequency. But when you run the machine or when you see the specification of the machine, you can see here it is L1 and L2. That means it is recording the data from two frequencies. So it's a dual frequency GPS receiver. From Sokia and from Trimble, sometimes you can see the receiver is connected through cable with to the processor, or sometimes you can have a wireless communication through antenna come receiver to the control unit. Here, this is a control unit to give the command, and here this is not an antenna. This is antenna come receiver. So receiver is also inbuilt. Sometimes you can see only 2 units are there. This is the antenna come receiver, and this is a control unit. So you require only 2. But here you see there are 3. Control unit is separate, receiver is separate, and antenna is separate. So you require 3 units. So these are up to you, the application. But this becomes more sensitive. They should not get fall down on the ground. If it is falling, then the receiver can break, and so forth. Third category of GPS is called mobile GIS GPS. Nowadays, like you see in your smartphone, that's equivalent to your mobile GIS GPS. You can have a background map and you can have the current GPS location. You can use it straight for navigation purpose. But here you can get more informations, like you can store the data as a point line or polygon. That's why it's called GIS, right? Mobile GPS means you can move very quickly and you can do measurements, so they call it mobile GPS. Actually it is mobile GIS GPS. Then you can record the point, line and polygon data. So here the old version of mobile GIS GPS instrument, you can see there is a palm top to be used, and then there is a external hardware for GPS antenna, and there is one software which can communicate between antenna and the palm top and can record the data as point, line and polygon. You can upload the any image or photograph on this palm top. So this is again very old technique which was launched, but nowadays you can see very compact, rugged, dedicated mobile GIS GPS instruments, and you can use them. The cost wise they may go 40,000 to 1 lakh depending upon configurations you are asking and so forth. The advantage is you can directly capture the data here as point, line, polygon. If you download the data, your data still has 3 layers: point, line and polygon. You don't have to worry about that. But if you are recording with a handheld GPS, the data is coming in the tabular form like 1, 2, 3 and X, Y and Z. So here you get lost. These 1, 2, 3 are of is a point, it is a line or polygon. It looks to be as a single coordinate. Second is positioning techniques, what we can adopt in the field. We can, for better accuracy and with different methods as per the application, we can go for single point positioning, or we can go relative positioning. We can go static positioning or kinematic positioning. Then in relative positioning you have sub 2 categories. It is real time or post mission. Single point positioning means you go to the ground and you just open the GPS receiver. It takes 1 or 2 minutes to get minimum of 4 satellites to be logged, and the moment it logs the 4 satellites, it starts displaying the coordinates. So that is single point. Why static? Means I'm standing on the ground and doing observation. That's why static. This is also called absolute positioning or point positioning. Why absolute? Because on the ground I'm not referring any other point, just locking the minimum number of satellites in my area and getting the coordinates. Minimum of 4 for 3D and for 3 satellites for 2D. Second is relative positioning. It can be here 3-4 words are there: relative, kinematic, real time. So here what is happening, the objective is to map the path of the ship with very high accuracy. So we have kept one base station at the point number 2 as a lighthouse, and the point number 3 we have kept second GPS as a rover. So both are on and both are locking the common satellites in the given area. So second is both are doing observation at same observation rate, say 1 second. Observation rate is defined, so every 1 second both are doing observation. And the distance between point number 3 and point number 2, practically it should be less than or equal to 20 kilometers. So once we fulfill 3 conditions, both are locking common satellites, both are doing observation at same observation rate, and the distance between both is up to 20 kilometers. Why 20 kilometers? So that environmental condition should at point number 2 and point number 3 should remain same. Hopefully it remains same. We assume that, and in that case what happens with fulfilling these 3 conditions, the error at point number 2 is common to error at point number 3. How we get the error at point number 2? Point number 2 is a known point. So, and the GPS is giving the coordinates every 1 second, but the coordinates, actual coordinates of point number 2 is known to us. So we can take the difference in X, Y and Z. So that means every 1 second we can get the error, and that error we can apply to point number 3 because they are fulfilling the 3 conditions. Both are locking common satellite, both are doing observation at same observation rate, and the environmental condition is same. So we can apply the corrections from point number 2 to point number 3. Then in that case what will happen? The accuracy of point number 3 will improve. So here I've shown you the case the rover is moving, but here this is a case of rover is static. So in the static in the forest, this is a GPS working as a base unit. It has a beacon which is connected on the tower and connected with this base station. It is transmitting the error in the air. Here this is a beacon which is working as a receiver. It is receiving the corrections and transmitted to the rover. rover here is on 2-meter pole, and both are locking common satellites. Both are doing observation at same observation rate, and the distance between base to rover is less than or equal to 20 kilometer. So we can apply the error from base to rover and improve the accuracy of rover. So it is basically your relative. Yes, it is relative with respect to base. Static, rover is static, and doing observation real time means actually in the ground itself the corrections are applied from base to rover with the help of beacon. Next is static or kinematic. So if I am moving on a car, on a foot, or on a ship or aircraft, whatever mode of traveling, and doing observation, then it's called kinematic observation, called kinematic positioning. Static positioning means I'm standing at a point and doing observation after locking the minimum number of satellites, then it's called static positioning. I hope my slide and video is coming fine. There is no issue. Still I have around half an hour. Let me try to finish. In the relative positioning, we can have two subcategories. One is real time. That means base is working and rover is working, and both has the radio link. The radio link supports to transmit the error from base to rover. So in the ground itself, the corrections are applied. That's why it's called real time. But if this application is not there, we don't require this application. We can go for post processing. That means base is working whole day, rover is working whole day. In the evening, we can download the data in a PC or laptop. We can use post processing software, and we can apply the corrections from base to rover. Same corrections here, it is calculated and applied in the field online mode. In the real time here we can go for post processing. That means our application is not so urgent to get the very high accurate data in the field itself. So that if that application is not there, we can go for post processing. So overall positioning techniques, we can have kinematic single point positioning here, then static single point positioning here. Here it is relative but kinematic, and here it is static. So here this is least accurate, more accurate, and this is the highest accurate. So if you draw n, so like that you can find out the least accurate and most accurate data from the positioning method. Some of the errors we can see before we go to the application side. So GPS positioning errors. So there are different errors like orbital error, how correctly the GPS coordinates we have calculated, how correctly satellite clocks we have. The signal is coming through ionosphere, so it is introducing the delay due to the ionosphere. There is signal is coming through troposphere. Ionosphere is basically charged particles, and troposphere is basically dust and water vapor content, and they introduce delay. At the receiver end, how correctly the receiver clock is giving error, how nicely we have taken care of the multipath. That means we are only locking the primary wave, not the secondary wave. How that receiver noise is giving error to the data, and antenna setup. That means how correctly we have done centering and labeling. So these are the different errors which are changing with respect to time, and that's why at different time, at a given point, if we do measurement at different time, we don't get the same coordinates. It varies, but that variation is within limit, right? And a lot of these errors we can remove through relative positioning, and that's why we can improve the accuracy in our data, because maximum errors are common to base and rover that can be eliminated through relative positioning. Multipath I have mentioned here. The signal is blocked when we are working to a high-rising buildings, because you are from urban field and you will be using GPS, and then you have to take care. This may happen and how to avoid it. But when we are close to high-rising buildings, we should lock the primary signal, but here we are getting the secondary signal also. So this can be minimized with the help of choke ring antenna or some signal processing methods. In the field itself, we should take care. We should not be close to the high-rising objects. If you want, then we can take the combination of total station. We can keep the GPS away from the high-rising objects, and we can do measurements of that object with the help of total station, and we can integrate the data from total station to GPS. Overall, you can see wide range of applications with respect to accuracy, what we can achieve. We can have accuracy, say 10 to 100 meters previously, which has been improved now. it is coming to around say 5 meters. It can be used for reconnaissance purpose, navigation purpose, and so forth. If my error in my data is around 1 meter, so you can use for GIS data collection, public tracking, emergency, and so forth. If the error is 0.2 to 1.5 meter, so we can use it for resource mapping, GIS database, utility mapping, highway surveys, and legal surveys, and so forth. If the error is less than 20 centimeter, around say 1 millimeter or around with plus minus 2 ppm, so we can use this data for geodetic infrastructure, fault monitoring, construction survey, engineering survey, geodynamics, and so forth, in urban cadastral survey, and so forth. Little bit with few terminologies which is there in the market, we can understand them, like global navigation satellite system. What does it mean? There are different constellation of navigation satellites. If we use all these constellations at a time, then that GPS receiver is called GNSS. And nowadays, as I told you last 1 decade onwards, so we are getting the receivers as GNSS. That means they can log the satellites from different navigation satellites. And if you see what are the different navigation satellites, it can be from USA, Navistar satellites, Russian GLONASS, QZSS from Japan, Compass or BeiDou from China, Galileo from European Space Agency, and parallelly we have space-based augmentation system. If we have one GPS receiver and we want the accuracy of that receiver from 4 meter to 1 meter, we can use SBAS satellite-based augmentation system, and in different countries it is known with different name. Like for USA it is VAS, EGNOS for European, MSAS for Japan, Gagan for India, and then few more from African and other areas for augmentation purpose. What they do, they improve they apply the satellite-based corrections to my GPS receiver, and the accuracy is improving from 4 meter to 1 meter. Previously, there was OmniStar, Starfire. They have established these corrections at the regional level. So here you can see the global constellations in the global satellites by different countries. GPS it require minimum 24 satellites. GLONASS require minimum 30 satellites. Galileo require minimum 27 satellites. Compass require 30 global and 5 regional satellites. Then VAS, if you talk the satellite-based augmentation system, if you see for VAS there are three satellites. For MSAS there are 2. For EGNOS there are 3. Gagan there are 2 satellites, and SDCM there are 2. Then you can see regional constellations. There are 2 navigation satellites which are working in the regional name, that is QZSS by Japan, and IRNSS regional navigation satellite system by India. This is also called NAVIC. This is also called NAVIC, name given by our Pradhan Mantri ji, Shri Modi ji, for NAVICs, basically the boatmen who are sailing for catching the fish, and this system helps them to guide them so that they can come back to the harbor. You can see the constellation of IRNSS. It has 2 type of satellites. One is the geostationary, which is at 36,000 kilometers, but making the inclination from the equator, it is 0. So these are the geostationary satellites, and there are 4 geosynchronous satellites, which are again at the altitude of 36,000 kilometers, but they are making some angle from the equator, which is around 23 degrees. And if you see the movement of these 4 satellites, they make a they make a 8 as a footprint on the ground in 24 hours. Gagan, how it works, there are, for India, there are some referencing stations. They goes on working, which are known points, and we are getting the coordinates from the satellite. So they find out the difference every 1 second. That difference is given to the master control. Master control upload this difference to a geostationary satellite called GSAT, and the GSAT transmits this error as a common error in the air, So wherever who has the GPS receiver enabled with Gagan, they can receive these errors, and their error in the data will reduce approximately 4 meter to just of 1 meter. So without doing anything, if my GPS receiver is enabled with Gagan, you can just switch on the Gagan. You can see your data accuracy is improving from 4 meter to 1 meter without adding anything else. Only thing, your GPS receiver is Gagan enabled. You can see augmentation systems for different countries like VAS and CWAS for Mexico, SACCSA for Southern America, EGNOS for Europe, AFI for Africa, Gagan for India and its surrounding, Malayas for this South Asia Pacific countries, MSAS for this Japan region, and SDCMA for European, for Russian sides. So this is the Gagan coverage footprint. If you see on the world map, very large area Gagan corrections are available up to this region. A goal of regional and GNSS civil interoperability. So we can convert, can we integrate the data coming from different satellites? It can be regional or from global. Answer is yes. So you can see here, specifically in the urban region, when you are mapping to a very narrow lanes, so it is very difficult to get the signal from a single satellite, and that too minimum we require 4 satellites. So if we have signals from other satellites, the probability increases to get the minimum 4 satellites. That's one. Second thing, the geometry of the satellite, whenever we are doing measurements, so 24 hours, the geometry of the satellite is very good. When the geometry is very good, the error in the observation comes down. We can understand the geometry, like if there are 4 satellites which are clubbed to each other very near, and then I'm doing observations, then what happens? Their geometry is poor. They are not well distributed. In the second case, the satellites are here like this, like this, like this, and like this. And again, if you want the coordinates of this point, the satellites are well distributed. So what will happen? The geometry is very good. So here the error in the data will be very less, and here the error will be very large. The error you can see through EPE directly in feet or meters. Expected positional error in feet or meters. There are some other parameters, DOP, which is displayed on the screen in the form of GDOP, PDOP, HDOP, VDOP, and time DOP. If you just monitor GDOP, it includes all. It includes basically X, Y, Z, and T. So with the help of GDOP, you can see how much is the error. DOP is basically ratio. It may be coming like 2. If it is coming like 2, just multiply by 2 again. So that is a thumb rule. So that means approximately 4 meter error is there in your data. So the DOP value should be as small as possible. So what we can do in the ground, we can give some time, say a few minutes after switching on the machine. Just after a few minutes, it established the connection with the GPS receivers, GPS signals, and the DOP becomes stable. Around 2 or 1.5 to 1.8 you can get if it is open area, if you are doing observations. And that time, if you record your points, the accuracy will remain very good. So thank you all. This is my last slide. Thank you slide. Any questions or query if you have, please let me know. I've not gone much mathematics, just given you overview, idea of surveying techniques, what we require basically if you want to locate what is it, what is that object, and where it is, its coordinates. So we can use a plane table survey or chain survey or theodolite survey. Best is nowadays people adopt the total station, which can do everything in the field at very large scale mapping can prepare. And then I went for GPS. What does it mean? The different positioning systems. It's first application for navigation purpose. With time, last 1 decade onwards, the GPS terminology has changed. People talk about now GNSS, Global Navigation Satellite System. Advantage of that is you don't have to wait to get the good geometry. anytime if you start doing observation, you can get a very good geometry. And if you have noticed, around 8 years back, when you were using map tool in your smartphone, it was giving sometimes GPS poor. That means that the geometry of the GPS satellites is not good. They're clustered to one area, and after some time the GPS quality becomes good. But nowadays, anytime when you switch on the map tool in your smartphone, you can start getting the accuracy within few seconds. Now there are so many apps you can download in the smart app, like mobile topographer. You can download that is a very good tool which can capture the data from different satellites. It is a basically GNSS tool, and it can capture the data from different satellites of navigation. Then it will give you the accuracy. Then you can record the coordinates, and you can get the better accuracy. There are options in that to get better accuracy from the same app. You can explore that. That's called mobile topographer. So nowadays, what I want to say, the technology has gone to smartphone. You don't require a very dedicated GPS. You can do a lot of work through smartphone also, using so many apps freely available. Some are freely available, some are commercial apps. So it's all up to you. And now this all. Thank you from my side for listening me. And now I can wait for 10-15 minutes for your question and answers. I hope you are able to see my voice, you are able to listen my voice, and you are able to see my PPT. So I'm waiting for the questions. One question, Subhadeep Datta, what is the actual term of positioning system, GNSS and GPS? So as I told you, I can just take one slide, maybe